Okay, welcome to lecture 2, the very last lecture of the semester. We're talking about imputation methods. We just got done talking about different ways to delete variables or delete cases. Now we're going to talk about filling in those missing values with estimates that we're coming up with. And there's tons of different imputation methods. We're only going to talk about some of them here and the most common ones here. These estimates that we're putting in can be based on either information from other people in our samples or information from that person on other information they filled in, which typically is the best option because we're using information from that individual as opposed to making guesses from other people that we have used. The variability will almost always decrease when you put in or impute a value for something that's missing because there's not a lot of variation when you're putting in a number that's based on another number. So most analysis involve understanding that inter-subject variability, so how much subjects vary, so that when you put in a value, it is the most accurate estimate of a value possible. And that will make more sense as we get in here in a minute. When you overestimate and you put in a number that may be too high or too low, then definitely that result is going to be pretty far off. So the first one we're going to talk about is mean substitution, and it is exactly what it says it is. You are replacing that missing number with the value of the sample mean on that variable, okay? It is the most used imputation method on the planet. Obviously, if you have a lot of missing variables, we talked about, like if you have 25% more cases that are missing on that one variable, you're probably just going to listwise delete it, just get rid of it. But if you have less than that, what you're going to do is take the mean of all those numbers and then impute it for those missing ones. And let me show you an example here. Here with the mean substitution, and we're looking at that first variable, the sum of all of those variables right there, if you want to have the mean, what you're going to do is take all of these other numbers, and we're dividing it by 9, because remember we have one case missing, so 1 minus 10 is 9. You're taking all these other numbers here, and you're going to add them up, and then you're going to divide them by 9, and that gives you 7.44. That is the mean of all of these numbers, and you're imputing that here. You can kind of try this on your own and take for variable 3, if you add up all of these numbers here and divide it by 9, then you'll get the imputed mean substitution number for case number 9 on variable 3. Mean imputation is the least desirable imputation method, but it's the method that most seriously underestimates the variance. You're really just putting in an average of everybody else, so it's not really telling us what occurs for that person. I'm putting in here, it is an available option with SPSS. Remember, SPSS is a statistical software program. We do have it at Clarkson on a couple of computers. Again, the reason we don't use it for this class is that for all of you to be able to use it, that would mean all of you having to report to 1 or 2 computers in the entire college, and I know your time is very pressed, so that's why we don't use an actual software program in this class. But it is something that if you have a data set, you can just use SPSS and kind of put in there, you know, to do a mean substitution. They'll do it for you. But it really should be avoided unless the percentage of the missing values is very small. And the other options really can't be used. So this mean substitution method, for the example we just had with the 10 cases, and you're kind of imputing a mean for that one case, that is not as big of a deal unless you had, you know, a lot of other people that were missing as well. So a subgroup mean substitution is a slightly improved variation of the mean substitution. We also call this the conditional mean substitution, but it is when we replace missing values with the value of a variable mean for a relevant subgroup. So let's say what you're doing is looking at a case, but only for women, you're going to impute the number of the mean for women instead of the mean for men and women combined, because that might have significant meaning if we parsed out those two groups. So if we looked out here, let's assume the cases 1 through 5 are women. So these top 5 are just the women. With a subgroup mean, what you're going to do is take these 4 numbers that we do have. Remember that the green is what we don't have. So we're taking 9, 8, 7, and 9 and dividing that by 4. And that is giving us our subgroup mean. Again, you can do that down here for guys and think of cases 6, 7, 8, 9, and 10 as guys. And what would be your subgroup mean if you take 9, 6, 7, and 7 and divided that, add those, and then divide it by 4, you would have your subgroup mean substitution for case number 9. So a case mean substitution is another imputation method. It involves using information from other variables for the same case to impute the missing values. Now here's the thing with a case mean substitution. These variables have to be related to each other in some way. It's not like you're taking a Likert scale on a 1 to 10 and then imputing that for a variable that might only have a Likert scale of 1 to 4. These have to be fairly relatable variables that you're using. It is the most often used to impute values for a missing item on a multi-item scale. So like I had mentioned on 1 to 5 or 1 to 10, but if it's consistently the same items on a scale. Works pretty well when you have up to 25 to 30% of values on a case that are missing. But again, when you have values that high, that's a concern and you'd want to dive into your information to find out why. So here we have a case mean substitution. So if we look on variable 1 through 3 are the items. Okay, so we're looking at here. The imputed value for variable 1, here on case 2 that's missing, is the sum of these two divided by 2. So again, we're assuming here that variable 1, 2, and 3 are pretty related and that they have some standardization between them. Now here's the thing to look at. Why this can be kind of an issue is that let's just look at case number 3 for a minute. And let's say that I had you do the same thing. Let's say we didn't know this was a question mark. If you were to do a case mean substitution for this person on this variable, that would be 5.5 when the actual value is 8. That's a pretty big variation. So we have a lot of variation with case mean substitution, and you're really assuming quite a bit when you're doing this. Regression imputation, there's a couple different ways to do regression imputations, and they're very complicated. I just want to mention them here as we've just kind of got done talking about regressions. But when we do a regression imputation, it involves using information from complete cases to predict what the value of the missing data would be. Now here's the thing, if you have a statistical software package like SPSS or Stata or SAS, it literally is a matter of putting in a 3-word command and it takes care of it for you. So when you have to do the math yourself, it is extremely cumbersome and can be very, very complicated. The variable that has the missing values is treated like a dependent variable. So all the other correlated variables become predictors. And again, you really have to have a good working knowledge of regression imputation to be able to do this. So here, variable 1, as we have here in case 2, is the predicted values of variable 2 and variable 3. And again, that can be kind of problematic because, you know, if we were to do this with case number 3, what would be our regression imputation for 8? It would be similar to that 5.5, 5.4 kind of region when actually, the number would be 8. So the equation for that is the variable 1, okay, equals 4.621 minus, and we're taking 0.734 times the variable 2 plus 1.139 times the variable for 3. And these are your regression coefficients. Now we don't have that shown here in this data set, but when you have those regression coefficients and you plug them in this manner, what you're getting is a 6.32. So if you're looking at this data set saying, hey, Amy, where did you get 4.621, 0.734, and 1.139? Those are all regression outputs, and we don't have that in this table here, but essentially that's what you're plugging in to get that imputed value. It can resolve a lot of kind of ways at looking at and developing more closely predictable equations, but again, you're filling in that missing values and then you have to rerun your regression. That would make sense if we were doing it in a statistical software program. But if you are doing a regression imputation is much more preferred than a mean substitution, because doing a regression, that's a specific kind of analysis, and this is an imputation method that is specifically designed for that analysis. It's very helpful when you have information that's less than 15% missing or missing at random, or when it's less than 10% of missing not at random. The other kind of regression imputation is a regression with error, or a stochastic regression. It's an extremely sophisticated way of doing a regression imputation, and again, something that with a couple of commands in a software program, it does it for you. But the approach involves incorporating uncertainty into the estimate by adding some random error. So what you're doing is you're plugging in coefficients, but you're also hypothesizing kind of an error number and putting that in. And that actually increases the variance. Remember, we had issues with that when doing a mean substitution because you're not seeing a ton of variance there. A last observation carried forward approach is the most widely used imputation method in clinical trials, okay? Not like survey trials, but clinical trials. And it's with multiple points at a data collection. So if you're doing longitudinal data, this is when you impute a missing value as a person's score as the same outcome of the most recent time they observed it. So let's, for example, say you are taking the blood draw or even temperature of a medication intervention after a certain number of hours. If after a certain period of time, let's say we do that on day 1, day 2, day 3, and day 4, let's see day 1's temperature for the period of time between noon and 1 was missing, you may carry that last observation from 11 to noon forward and impute that as the same temperature, okay, given that no new intervention was given. That would be a last observation carried forward approach. When you're imputing from baseline scores, maybe you have just baseline clinical trial scores, that sometimes is imputed as well, and that's called a baseline observation carried forward approach. So just to kind of give you an example, let's assume that we have an outcome measured at 3 time points, time 1, time 2, and time 3. What if the last observation carried forward at the time 3 value for case number 9, so if you look down here, we impute that. So here we've had, this was their score at time 1, this was their score at time 2, and we carried this forward to time 3. That same value would occur from time 2 and time 3. Now what you have to think about is, what if time 1 is missing? Do we carry forward time 2 or do we carry forward time 3? And that really has a lot to do with what you're measuring and how important that is. Let's say you're using time 1 as a baseline score. You can't really use this case if the baseline score is missing. So in this case, in a time kind of temperamental approach, you might just get rid of this case in its entirety. So a last observation carried forward has this implicit assumption that the outcome did not change over time, which is making a really large assumption. And it sometimes is a very conservative estimate of the treatment. And you're kind of saying no change occurred in this treatment, which makes a lot of assumption about the treatment in itself. This actually was the most previously preferred method by the Food and Drug Administration for trials of new drugs. So that's something to think about, in that for testing of new drugs, this last observation carried forward really assumed that no change occurred. So obviously there's some errors that could occur just in that alone. There's some variations of a last observation carried forward, and that can be used when there are many time periods. So for example, if you want to use the mean or the median of a person's prior values, so at time 4, let's say you wanted to look at time 1, time 2, and time 3 divided by 3. So you're actually taking the mean of the last observations. That could also come into play. Or maybe it's that interpolated value where we have values for time 1, we have values for time 2, but we don't for time 3, but we don't for time 2. You take time 1 and time 3's values, add those together and divide it to get time 2. Last observation carried forward can be used for outcomes on any measurement scale, but most of the time these occur when you have ordinal level data, and you can use it in that manner. Worst case imputation is another method. It's pretty controversial. It's very conservative, and it's kind of assuming the worst case scenario. So when you have these kind of imputations, this is when you replace a missing value with the worst case scenario for a categorical outcome. So let's say you're using 1 and 0 for fall status. So a person fell versus they did not fall. What you would do is you would replace the missing value. If we didn't know if they fell or didn't fall, we would assume the worst case. We would assume a fall. In that scenario, you really typically have research assistants that are being very vigilant. Is that the word, vigilant? No, that's not the word. Very militant about collecting all the information because they don't want to put in the worst case scenario. They want that information, but it is extremely conservative and it assumes the worst. You're not going to have kind of biased outcomes as much. Best case imputation is just the opposite of that. You're replacing a missing value with the best case scenario. So when you have a fall versus a did not fall, you're actually replacing the missing code or missing value with a no fall. This can be used together with the worst case imputation if you want to estimate a full range of possible treatment effects. So let's say you have 100 cases, you have 5 that you don't know if they fell or didn't fall, and maybe you do 2 didn't fall, 3 did fall, and you kind of impute equally or as equally as you can a best and a worst case scenario. I'm going to talk about and kind of breeze over this expectation maximization idea of doing an imputation method. It can be extremely confusing to listen to as I try to explain it. This is one of those terms that's kind of very helpful when I have you guys in class. But some of the best missing values approaches uses the maximum likelihood imputation scale. And it's often referred to, if you're looking in your reviews, it might be referred to as the ML algorithm or called the expectation maximization imputation. That is a really great phrase there. So we'll kind of title it EM for short. The expectation maximization imputation is available in SPSS, so it's very easy to do. It's a 2-step process. In what we would call the E step, the expected values are calculated based on all of the complete data points for a person. But then in the M step, the procedure imputes the expected values from the E step. And then it obtains this maximum likelihood function to obtain these new parameters. Then, oh sorry, I went back. Then those new estimates are substituted back into the new E step. This is a two-step process, and it continues until it changes into the expected values from one iteration to the next trial. Now again, this is kind of a hard statistical formula, so in an SPSS or a STATA or a SAS program, it's literally 3 words, and it does all of these steps for you and redoes the step for you. So the EM imputation produces estimates only with small amounts of bias, and it typically is only done with a statistical software program. So I am not going to ask you to do this on a quiz. I just want you to be aware of it. And just to kind of show you here, in doing this imputation on a SPSS program, the value here would be 6.37. Why that's important is I just wanted to kind of show you that strategy really matters. Different methods show different results. So, you know, for these different kind of using leastwise deletion or a mean substitution, a leastwise deletion, we're just lowering our n. We're taking out that case completely. So we don't have to really worry about this value at all. But just look at the variation in what we get for using these different methods. For a mean substitution, and we have 7.44, that's much different than a subgroup mean, which gives us a much higher rating. A case mean, where we're looking at just that individual, yields us 6.50. And you can see here how our overall mean for all of these scores change. If you use the regression imputation, you're doing a regression, the mean for the overall group is 7.33, where the mean for the overall group, if we do a subgroup mean, is higher. Now these points may not seem very important, but it definitely changes our standard deviation, and it has implications for our statistics in the long run. So even though we're, you know, some of you would say, you know what, we're all in the 7s, we're good. Overall, it can have some pretty big impact on what we do. You can definitely do a single imputation. All of these methods that we've done so far are examples of essentially a single imputation. And that is just where we take a single estimate and we impute it and substitute it for a missing value. All single methods share the same shortcoming. They don't address the uncertainty of a single estimate. These estimates are just exactly what they are. They are estimates, but when we plug them in and we put a number in for a value that's missing, we're treating it as if it's a real value. And that can be very, very problematic. When we do multiple imputations, which is quickly becoming the gold standard approach to handling missing values, we essentially are using a computer program, a computer package with a very complex data system, and it's not widely used because you really have to have very specialized statistics. We're plugging in numbers that the computer essentially is drawing at random as close to the actual number as possible. So it's great, it's definitely the gold standard, but it's extremely time consuming, and you have to really either be at a large research institution where they have the software and have definitely a very large data set. Multiple imputation, just so that you know, is a 3-step process. You take the maximum likelihood estimation algorithms, and the missing values are replaced with those estimates in a new data set. So you're actually recreating a whole new data set with imputed values. Then those imputations are done over and over and over again, just to see how often, let's say you redraw that same data set with different imputed numbers 5,000 times. Over those 5,000 times, the computer is going to estimate 5,000 times on variable 1, this was the mean. And you pick as close to that number as possible. And then, once you do those over and over and over again, 3 to 5 times is acceptable for a good solution if you have less than 20%. But if you have more than that, they expect you to redraw and redo that sample over and over and over again, probably more than 10 to 15 times. Then that substantive analysis is taken with the number of data sets you've done, and the results from all of the analysis are pooled together. So when you have like some data, some kind of missing information, and you throw it into this data and you rerun it, and then you do the analysis, then you take all the same data and you plug in new numbers and you rerun it, and then you take it again and you plug it in and rerun it. From these three analyses, then you make one large analysis, and that's your actual outcome. You can only do this with statistical software. Some of you may think, you know what, I'm really good at math. It's not about being good at math. It's about redrawing an entire new data set over and over and over and over and over and over and over again with new numbers, doing the whole new analysis, and then coming up with one pooled result in the end. So it can be extremely, extremely cumbersome. It definitely assumes missingness is missing at random, and the assumption of missing at random is actually unlikely to be precisely satisfied, because sometimes there is a reason why information is missing. Some researchers believe that this is very realistic, but it also is kind of getting away from the missing at random, because it's not likely to validate how many times you go over and over and over again in the large analysis that you're doing. So after we've learned about all of these, what are we taking home from this? Well, you really have to learn as much as possible about the amount and the pattern of missingness. You need to take the steps to understand with the missingness where this is occurring. So within the variable itself, who is missing in that variable? And for that person, how many other variables are they missing on? This is extremely important, because a very basic requirement in understanding missing values is you have to be sure that all the variables have appropriate missing values code. If you're running a large analysis and you don't take care of your missing values, you are going to come up with extremely, extremely wrong answers. So it has to be looked at with every single variable. You have to make sure to understand why something is missing. Like, did people refuse to answer the question? Was there an illness? Those things are completely different issues that could be going on. You really want to conceptualize the variables that could predict the missingness. So for example, age, sex, illness. You know, are you asking age in a way of what year were you born? Or maybe you want to know the spouse's age, and you're asking what year was your spouse born? I can tell you how old my spouse is much faster than I can tell you the year he was born. So it's just a matter of understanding how are you asking the question. And then conceptualizing again what the variables that could be used to predict other variables with the missing values to really get as close to an estimation as possible. So make sure you select the most optimal strategy feasible given all the factors involved. There is no way that you want to do one of those multiple imputation, computerized, large kind of processes when you have 50 cases and they're all surveys right in front of you. That's probably something you could do yourself. And if possible, look at all of the alternatives and figure out which one is best. Is list-wise compared to pairwise best? Is worst case scenario versus best case scenario, you know, which one is the best? You have all of these options in front of you. You really want to look, and when you look at your articles, see if they provide that rationalization. We utilize list-wise deletion because sometimes people take very good care of their missing values, and they take the time to explain what they did and why they did it. With frequency distributions, when you indicate on a variable by variable basis what number and what percentage is missing, that sometimes is helpful to have the people in your study know. So be sure to consider whether some cases should be excluded from the tabulations completely. So if you have percentages with missing data on the number of pregnancies, and you have one that will be half and half, and the sample is male, then that's something to consider. Look variable by variable. The inspection may be may help to identify the variables that could be detected. So it might not be an issue that you have all these missing datas, it's just that men are not going to put how many times they were pregnant. You might have men that do put in a number, but they're thinking of their wives, how many times do they have a spouse or a significant other that's been pregnant. So you will have men that put a number on number of times pregnant. And then the last thing to keep in mind is that missingness within cases should always be examined. When you have one case that's missing a lot of information, you may just want to drop that one case. You may not just list-wise delete everyone, but you may list-wise delete that one case. And a case with 90% of values missing should just be dropped. That's not going to help you. It's not going to help your data. That one survey should just go away. And then how to detect missingness. There's a whole different manner to go through. Your book does talk about it. When you create an actual variable that is a missing value variable, and that collects data on all the missing values, and that can be very complicated. We wrap up this course with the most important object, or subject rather, of statistics, which is taking care of our information and taking care of our data and making sure that we're telling the most accurate story possible, because that's the most important thing. And I just urge you, whenever you read an article either in the newspaper or in the journal, find out how many people are in their sample, and are they looking at a good picture of the population, or are they only looking at white females from the Midwest? That's not telling us a very descriptive pattern of information if we want to know about all of the United States of America. I hope you've enjoyed the class. Please let me know on your end of the semester evaluations. Some very constructive feedback is very helpful. What was helpful with the class? What was not so helpful? What are things that you would like to see either improved in the class? What were things that really worked in the class? All of these things are very helpful because I typically don't leave weeks open. I'd like to know if that worked. You'd like to be able to go back and listen to the lectures. That really helps me to improve upon the class. So thank you so much. If you have any questions, let me know, and good luck on your final quiz next week.